I'm nervous because I didn't expect so many people to show up at a compiler plugin talk. My name is Mohit Sarveiya, and I am a GDE in Kotlin and Android. So I'm going to present on how Compose works underneath the hood. In this presentation, you'll get a full bullseye view from how things work. So, by the way, this is my first time presenting at this conference, first time in London. It's been great here. So, I'm going to share with you is the Compose architecture, and what are the components in this architecture? What does the API look like? So, I'm going to share with you. There's something in Compose which is called a slot table, and I'm going to share with you how it works. I'm going to share what the compiler team has been exploring, and what I'm going to share with you is recompositions and how they work underneath the hood. So, and also how IR code is generated. So before I explain to you something, so another thing is that at the half of this presentation or at the end, I'm going to walk you through step by step the code of how things work, how things are structured in the Compose compiler plugin and the Compose runtime. So get ready. So how many people use Compose here in production, have used it, and know? That's good. Everyone has a good base. Most people have a good base and starting point. Before I start, I want to give you a first sneak peek at what I'm going to be showing you. So this is the Kotlin compiler source code. So in this Kotlin compiler, what you're going to see is that this is an example of a test. Could everyone see this? All right, that's good. Let me zoom it out, zoom in more. So this is an example of a test of a very simple composable function called test. It's calling another one. What the compiler plugin does is that it basically transforms this code to look like this. This is the same piece of code, but you'll see there's other information that get added. The composer, we're creating a restart group. I want to go over what that means. So this is a test which basically does an assertion that this piece of code right here, so the way this works is that this method right here tells the compiler, I want you to transform this piece of code right there to this. And it does an assertion that the transformation was correct. So this thing over here are key pieces that make Compose run. This is hooking into the Compose runtime. And I'm going to explain to you what do these things mean. So let's start. So at the other half of my presentation, I'll walk you through all that. So what's the benefit of understanding Compose? So as a client-side developers, when we build features, we use Compose UI, which is something that's different. So the underlying layer is a logic and architecture which could be used for different use cases. And what's good about this is that Compose is actually just a library for managing a tree of nodes. And it has nothing to do with UI. And a lot of people have that misconception where you hear the word Compose, you think of UI, but UI is just an application of it. So when you look at this tree, like in the UI, for UI, the context could represent like text and rows, but it could represent other things, right? And I'll show you examples of other things that I have worked on that I have used where I've used this. So there's a library called Molecule. How many people use Molecule? So this is great, one person. I'll take that. So so Molecule's library built by Cash App. I've used that there. So Molecule is a library that uses the Compose runtime to set up your business logic. It has nothing to do with UIs, but it's built on top of Compose, the Compose runtime. So that's an example of it. And so this is an example of using Compose, not in the application of UI, but more setting up your business logic. The library provides an extension called launch molecule, and over here you have a composable function where you would put this in a presenter or a view model where you have logic to figure out how to create your UI state. And what this does is that this library creates a state flow. Every time this thing recomposes, it pushes to that state flow using compose runtime. So this is an example of thinking outside of the box, right? And in order to build this, the underlying source code for this is actually very simple, which I'll show you. And it all leverages this knowledge of how to set up compose to use it in different applications. So how many people have heard of Circuit by Slack? Good. So that uses this molecule. That was inspired by a lot of the things that we did at Cache. So there's another library called Mosaic, which is used for building terminal apps, for Compose. What a name. Mosaic is a good name. So you could also do server-side rendering, and I have done that too. So there's a great article by a wise man who wrote about, what I'm talking about, which is, the nomenclature. Like compose doesn't really mean UI. You could use it for different applications. When you go underneath the hood, you got to get granular. And so this also gives you some foundational knowledge. Now, another thing is that a lot of what I'm going to talk about is not documented anywhere. I mean, this is reverse engineering, and you just start exploring about how things work. And so let me start with something. Let's start with the source structure. So this thing here, ASOP, is called Android Open Source Project. Has anyone worked on that? Or like two people, I'll take that. So I recommend that. And the Android Studio source code is in there. All the Jetpack libraries and the Compose runtime sources in there. So what it contains basically is are the source code for all these components. These are the components that make things happen: snapshot system, recomposer, and composer. So there is another piece to this, to understanding Compose, is the compiler plugin. So this is the JetBrains Kotlin compiler repo, and in there is where the plugin is. And the plugin used to be in this repo, but they moved it out, which is a good thing. And all of these things, these transformers, they generate code to be able to hook into that, like I was showing you. So in order to, these are two things to understand. These are two difficult things to understand. They're difficult because when you look at the architecture of these things, this is not like clean architecture or anything. This is like simple, because this is a different world where you're not building an app, you're solving a problem. The way you're architecting something to solve that problem is a different approach. You're not going to find repositories and interactors or anything that you would find in an Android app. So this right here is where IR code, IR transformations are done to be able to hook into that. In order to fully understand things, in order to fully understand Compose, at bottom of the hood, you need to understand both of these things, because you need to understand what a composer is and what it means to do what a restart group is. So what the benefit that this knowledge gives you is that you'll be able to do a lot of creative things. So this is what the Compose architecture looks like if we take a step back of 1,000 feet. So this is not like an Android app architecture, is different, is that all of these pieces here have an API associated with them, and what they have, these are the components in there. When you look at this library, there is an entry point to Compose that you could hook into. Compose UI, Molecule, all those libraries, they hook into this composition object right there. When that kicks off, it has to tell the recomposer to do something. You have to tell the composer to do something. So this is the high-level architecture when you take a step back. And now we're going to go into what are these different pieces and what are they doing underneath the hood. So as an Android engineer, you come across a recomposition issue and you go into your debugger, you'll see like these things. You'll see, for example, a recomposition scope instance in there. So this is good for understanding what those things are. So here's the thing. So I'm going to start with the slot table. So the current implementation of a slot table is using something called a gap buffer. Now, what I'm going to present to you is something slightly different, So in the compiler team and has been working on exploring how could they improve the performance of recompositions of compose. So in Android open source, it doesn't use GitHub, it uses this, which is a different style of doing things. So this is a PR basically which benchmarks different explorations of how to implement the slot table, the underlying implementation. So they benchmarked, different ways, and they explored these different ways to be able to architect, explore different implementations of it. These were some of them. So and you could go in and look at that. So this is a implementation that was explored by Andrew and Chuck and Leland, and shout out to all of them who work on the compiler team and on the compose team. So this is a PR that was is no longer open. This is a PR that exposes, as you can see, a linked list as data structure for implementing a slot table. So that's something good to know. So even though the underlying implementation changes, what's good about this is that all these components abide by an API. So you could change the underlying implementation of something and test it out, how it hooks into different things. So now let's get into the basics. What is the problem that we're trying to solve? So imagine this. Let's take the context of Compose UI. You're building a UI layout, and it looks like this. You got a row, column, etc. What does the slot table do? What is the purpose of it? When you look at this hierarchy, there's a lot of information that I need to keep track of. I need to update that information when a recomposition happens. When you look at how to solve this problem, this is a data structure problem, right? You have to think about performance. You have to think about your memory allocations, and there are different ways to solve this problem. This is a problem that's different than usually as a client engineer you would face, and it's a different way to think about a different world. So every node here is a group. The word group is synonymous with a node in this tree. That's when I say group, what I mean is a node. So that's important to know. So the one thing that we need to keep track of is the relationship between these groups. Imagine you had a column that had a row internally in there. There's a parent-child relationship of those two things that I need to keep track of. The question is, how do I keep track of that information? So there's a parent-child relationship there that I need to keep track of. I also need to record any state dependencies. For example, suppose I had some mutable state like this, and I needed to update only these nodes. I need a way to go through this tree in a fast way with performance and just to update the information, like these nodes depend on that state. So how do I do that? And that's where recompositions come in. That's where things come in, like skipping a group, So how does that work? So all this information about that tree is recorded in a slot table. And the way that there's a way, an API to build this slot table, to build this information. And the good thing is it's all behind a builder. So this is an internal API. This is not external, but when you go into the Android open source project repo, you'll be able to explore this. You'll be able to do this. This is building a very simple slot table, and the slot table actually looks like a table, and it builds something called an address space. So when this code executes, this is the code that executes when you go, during initial composition, your app starts up. So what does this do underneath the hood? It builds a linear table like this. It has a max size of 64 slots. Each slot in here represents a group in that tree, and it has an address, which is, in this case, a hex value of 0. And it has a key, which is arbitrarily assigned by the source code, by the Compose runtime. So it starts off as empty. I have this as an example just there. So we're going to store that information, all the information in here. And we need to be able to traverse this when recompositions and compositions happen. So here's an example of storing a group, a node like this, which has an arbitrary value, key value of 37. And when you execute this, it, it shows up, it stores like this. Now what this represents contextually is, again, it's part of, it's all based on what example you're using this in. In Compose UI, this could represent a particular row, for example. In Molecule, could represent a composable function. So that's the API. I have a marker there, start group and end group. And when I add more and more groups and this gets filled up, another page gets created. So imagine this being a table of contents where each entry is a particular group and it links them together. All of these pages have offsets, 0, 1, 2, 3, 64, and then this offset starts again. So this is the basics important to know. So we're going to build upon that basic. Now I need to be able to track relationships. So there's a concept of a group having metadata, which is extra information. And how do you create a group that has a parent and child relationship? So what I'm doing here is nesting these start group and end group calls in between this. This right here is a child group, and that right there is a parent. This could, as an example, like in Compose UI, that could represent, for example, a column, and in the column inside of it, you may have another element like a text. So this is how you establish. I'm indenting this just for visibility, but the start group and end group markers are nested. So this is how you create a relationship in the slot table. So, and it looks like this. So every time you add, no matter what relationship you have, all the groups, they get added linearly like this. But then the question is, for this group, how do I add information that's the parent of it? How do I do that? So, sorry. If I fall down, that would be so great. It's the first. And every group has metadata. And so here you have the hex address right there of the parent. The parent for that is null, but it has a child, which is a 1 right there. That's so. Imagine if this group right there, imagine you had a composable function, you were giving it a string value, and you need to store that string value somewhere, right? Where do you represent that for this group? In this metadata, which I'll show you. You need to store that because when you do a recomposition, you got to go into that group again, go into its metadata and update it. So here's an example of how do you store primitive values. Imagine this represented a sample, composable with an int value like that. How do you store the computed value? There's a method you could use to append primitive values to a group like this, which is append value 1. So what this does is that this thing goes in there. You have the group right there. You could store more values in there. So this right here is a new linear array, which has max size of 64. Is different than the previous table. This is only for storing primitive values, so all the groups share this. So let me repeat that because that does get complicated when you first learn about this, is that this group is just for storing primitive values for each of the groups. So 1 and 2 right there, you can see group 0 is 1, group 2 is, if I had another group and I append a value to it, it was stored right here. So it goes from up to the bottom. So this is shared between all of the groups. This right here. And that's how things are stored. So this right here is how you store, for example, this is a separate group. You can see right there, I'm storing in the same slot table. So this is called a primitive slot table. What about, so in the end, when you look at, the metadata for this, all the primitive values are stored in these slots right here. And all of them have an offset. These primitive slots are all shared by these groups. I might be repeating information because repeating is good. It's good for recollection, I guess. So what about when you have primitive values like a string? a primitive value like a string, it has its own slot table called a reference slots. So you have imagine like sending that to a composable function that gets stored right there. And a similar concept here. So there are 3 slot tables, one for the group, one for primitive values, and one for reference types. So this looks like this underneath the hood. By the way, how do you as an engineer explore this? You could go into the source code. You could do slot table dot dump slot table dot build debug string. And when you could print that out, and what that's going to do is show you what this looks like. Could you do that from your debugger? No, because this is an internal API. But if you want to learn how this works, you could go into the source code in the slot table test and do this. So, so this is down. The second group looks like this right there. So how do you read groups? So when a recomposition happens, you press a button and you got these other UI elements that need to update. So you got to be able to read the group from up all the way to down and go to the right group. So how do you read it? So there's a builder there for that, which looks like this. This is an internal API again, slots.read. So what this does, the way you read groups, you start with a marker. This thing, when you call read right there, you start reading from the top to the bottom. You can't really jump that easily. You can't jump. I'll show you a variation of how to jump, but you have to start from the top. This is what happens when a recomposition happens underneath the hood. So you start with start group, and it goes to the first one. And then what it has to do, it has to go to basically the second one. You could print out information as you're reading, like a group key. You could print out what's in the primitive slot. There's a lot of information you could print out right there. Then what you could do is basically skip a group. This is important to know. This is what happens. When you saw that code, IR generated code, at the bottom you had a composer.skip group. That's what this is. This is skipping as you're reading that group because it doesn't require any updates. So that right there is the API of the slot table. This is how you skip a group. So you could also print in more information about other groups, as I'm doing here. So the question now, those are the basics of the slot table. There's more stuff, and I created a YouTube playlist for this that I'll show you later. So the component that starts everything, initial composition. When you do initial composition, like your app starts up and the layout, you see the layout. During the initial composition, your composer is the one that's creating these groups. This is an important piece of compose right there. So how does that work? What does the composer do? So this is the thing that I showed you before that they're working on. So what I'm going to show you is a very simple example of this. How does the initial composition happen? Initial composition, performance-wise, is the bottleneck of performance. And you have to go through it because Compose has to look at your stuff and record all that information. So this is a very simple thing, composable. This is in the context of Compose UI. What happens? How is all the information here recorded, and when you change that name, how do these things get updated? And that's the question. So how do you explore that? So these are 3 goals. This is a flow. This process is a flow. Initial composition, it has 3 goals, and these 3 goals are important. You got to hook into the snapshot system, which is a way to know whether an invalidation happens. You have to set up recomposition scopes. You have to set up all the groups. And I'll go through one by one what these things mean. So there are a lot of great talks that go into looking at Perfetto, using Perfetto to look at traces. And when you look at those traces, you'll see that the composer is spending a lot of time doing something. What is it doing? So these are things that it's doing underneath the hood. So this right here is the entry point of Compose. This composition object. So Compose UI and Molecule, anything you build has to enter through there, and that kicks off the process of initial composition. When you do set content, it tells the composer to start. So how does compose UI and other things start up? There's a pattern here. When you look at this pattern, when you look at either molecule source code, if you look at the compose UI source code, the first thing that happens is that it tells the recomposer to start listening. The recomposer is important component of it. And by the way, this all of this is complicated. I want to acknowledge that. It takes a lot of effort to understand this. So the first thing that happens is that it has to tell the recomposer, I want you to start listening to any invalidations. So this is a method. So when you look at molecule, you see that it calls this method before. You have to set this up, run recomposition, scope, and apply changes. What does that do underneath the hood? Underneath the hood, it starts listening to the snapshot system to tell it what changes is going to happen. And this is in the source code happens. It registers an observer. So when you press a button and the recomposition happens, what recompose? What group needs changes? All that information is here in this change right there. This is the invalidation that gets passed in. So I have to start the recomposers to start listening to that snapshot system. So that's the first step. That's the common pattern that you're going to see. So the recomposer has different states. It starts off as inactive. Suppose a recomposition happened, it's going to go through all of these different states. You could listen to these states by collecting from that state flow. So this is important. So when you go in your debugger and you are like debugging a compose issue, you'll see a recomposition info object, and you could use that to basically get this information. So it looks like this. This is a state flow with these stream with the state changes. And right here, this is an internal API. And you could collect from it. And what this state object has is what it's doing underneath the hood. What is the state of it? You could also get information on what was invalidated from it right here. So the compose code, what it does is that when a state change happens, it will start to recompose. So this is the first step that happens, recomposer. So next thing that has to happen, and this right here is important to understand, you'll see this pattern again. This is the entry point, the composition object. This is the orchestrator. And I'll go over what this is, and I'm injecting in a recomposer. You all know what this is, right? Set content. This right here is the thing that starts the initial composition, starts the whole process. This tells the recomposer, I want you to start populating the slot table with all of this information. So how does that work underneath the hood? So molecule, for example, does the same thing, but it doesn't use a node applier, it uses a unit applier. But it also sets up a recomposer right there. So it also does this too. So this is a common pattern of how compose is set up. This is the benefit of knowing this, is that you could build tools like libraries like molecule, which was built to solve a problem. So the way it works is that this is a story, right? I just set this up by telling you a story about the compose runtime, which is what you need to know as a prerequisite. This is a story to understand this world right here. This is why the purpose of why this was built is to go into the runtime, is to start hooking that process up. This is a different world, well, also a complicated world, because this is dealing with IR transformations, which is also undocumented, which I'll go over at the end of this presentation. What is the IR transformation doing? Your source code, when you had this greeting right there, the compiler plugin takes that, converts it to a PSI, converts it to FIR, which is a tree, takes that and then tries to convert it to backend IR. All of these elements, the way it does is that it modifies that IR tree and it adds transformers to add in this, and this. It has transformers to do that. So there's a purpose to why that's doing, and you understand the purpose if you understand the runtime. So this right here is telling, as you can see here, now you know what a group is. It's telling composer to create that group with the key in the slot table. And so basically, this right here is code which is also hard to understand at first, but what this is that this is the skipping logic that goes into it. And then it calls other composable functions that you have. This is the function body. What the compiler plugin does is that takes this right here, and then I need to wrap my generated code around that, and there's a method to doing that. This right here is skip to end group. So you already know what skip means, right? Skipping as I'm reading that slot table. This is what that does right there. And so now you can see we're fitting pieces together to understand this. So that's what the compiler plugin does. You know, it uses the IR API builders to be able to do this. So it has a set of transformers to be able that accomplish this goal, which I'll go over. I want to skip this. This is good stuff too. This right here is a facade that hooks into the compiler. The compiler has like APIs now to do analysis. So I won't go over that. What I will go over is what happens how is the slot table created? So this thing right here kicks off the composition, and it tells the recomposer to do something. The first thing that happens is that no matter what you build and compose, there's a root group that gets created with a hard-coded root key. So this is the source code in runtime. Do compose is the thing that kicks everything off when you call set content. And what this will do when you look at this code, it will go in and create this first initial group right there. So there's always a root group. So, and then it goes in basically and it creates another group, which is a child group, and there's a hard-coded key of 1,000. And what I want to explain to you is that the important things, when you call set content, that lambda is a composable. It gets converted to a function type, and it will store basically that composed lambda instance right there. Everything after this, what it will store are basically the information about your actual composable functions, and I'll show you that. So right here, you can see this lambda right there is a function type. The next thing that it's going to do is right there is going to invoke a composable function. So it's going to call this method. What does this method do? This is the method that hooks into your actual code right there to start calling like the generated code from the top to the bottom. And what that does is that it looks like this. So it calls this method right here. What this does underneath the hood is that it's going to create a scope. It's going to create a group as we looked at. So you already know what this means. It's going to create a group in the table, which looks like this. So this right here is your greeting method right there with the group address of 2. Then it has to store some values in there, which is going to be a recomposition scope, which is important for recompositions. So what it does is that recomposition scope is just an object that stores in the scope and the group address information. This is a component in the compose runtime. And what this does, it has a lambda. So when a recomposition happens, it needs to invoke this again. That's why it stores that information and pulls it out, basically. So that's how recompositions work underneath the hood. And also tracks any state that you have in there. So the one thing that I want to go over is very, very important is that when this object gets created, it stores basically the group address. And this is important because when I do recompositions and go through the group from top to the bottom, I basically have to pull out. This is very useful to me as I'm going from the top to the bottom to know what group to stop at to update for a recomposition. So this is important information that gets stored in a scope. So what it does is that this thing updates the value. So what it does is that what that update value does is that it goes into the reference slot and it stores an instance of that recomposition scope. If you had this composable with other information you're passing in, like a name, a string, the computed values get stored in this reference slot. So, so the next thing that happens is that you can see here, right there, is the storing more information. What is the computed value of that hello, which is hello Bob in this case? So that was important. The next thing that happens is it traverses down and it creates like groups for all of these composable methods. And so it's the same piece of code. So you started from the top hierarchy and you went down. And what this is telling the composer to do is the same thing: go in the slot table and create more information. So you can see that's why this needs to be passed all the way down in your hierarchy. So that's the purpose of passing this information right here. So that there's a purpose to everything, and that's the purpose of it, to create that information. So at the end, this for user bio user detail. So this is greeting, and these are the other two composable functions that it calls. These are the children. This is the parent right there. So this is how things are stored in the slot table. Okay, so I have 5 minutes. So in the reference slot, you look at this, and you see that this information gets stored. So in the end, when initial composition completes, this is what it looks like. This is a very, very simple example where you have your reference slots right here. You have a recomposition scope for these two things right here. So when a recomposition happens, I need to be able to traverse this, go from the top to the bottom right here, and then go here, and then do an update on the information that was changed. And I'm able to skip these things because the snapshot system tells me, what group is affected. So because I have 10 minutes left, I'm going to stop right there and show you now how this world right here works. So what I just shared with you is the compose runtime. This is the Kotlin source code repo. I recommend going through this repo, and this is broken down to different pieces. This is the analysis piece. So when your source code, the Kotlin compiler takes that, converts it to a PSI tree, and then figures out where's your syntax errors happen. Where's all that happen? It happens in analysis. The K2 compiler, the benefits that it provides is that right there has an API that you could hook into now. If I had time, I would go over that. So what is the entry point of a compiler plugin? This is the one. You can see here it has transformers that it sets up from the top to the bottom. This has to be done in order because this has to be called first, then the other transformer right there. So what a transformer is, what it looks like, I'll show you this example. Let me share with you this. So when you look at this code right here, right? This test right here, there's a transformer whose specific responsibility is just to do a transformation on that parameters right there, but nothing here. There's another transformer whose job is to basically do everything inside of the function body. So each transformer has a specific responsibility. So what does a compose param transformer comes in? This is where things get fun. So this right here is a param transformer. And what it does is that it inherits this right here. Every transformer inherits an abstract class. Now you could argue that this is built using inheritance, but I won't argue that here. So this right here has extensions on how to do things. And what I want to share with you. So you saw in this generated code right here that it's adding a composer right there, parameter. How does it get that type? So this is how it gets that type. So this right here, context, is an interface that allows you to reference things. So it's referencing a composer object right here. And this is something that's reusing for every transformer. This right here is an important abstract class because this is kind of like a wrapper around the IR builders that it provides. Now, there's a module right here called IR tree. So the compiler is broken up into backend and front end, and I can't find that module, but it's important to know that module because you can see right here. Oh, let me show you. This is the good stuff. So IR, there's the API to build IR elements. So this right here, you can see is called native module, and there is something called Swift IR. This is something that's built out right now to be able to support Swift export. There are bridges that are able to take the Kotlin code and be able to convert it to Swift export. There's a branch which is open right now, which has a playground that you could play around with. So this is part of native. There's also a way to do that for Objective C. So which is how Objective C, which is right here, you can see Objective C header generator. Our Objective C artifacts get generated. So what this prints, what the most, I'll give you an example of some of the good things in here, which is, let me see, right here, IR call. Oh man, look at so many great extensions are here. So this is a really nice utility. It's a helper method. So this right here is how you create a function call. Like when you do composer dot call some function, this is what that does right here. This creates an IR element. That thing right there is the actual builder that you could use. Now, none of that is really documented how that works, but it's easy to understand the source code for it. And I want to stop right there. That's what my presentation. I hope that was. I want to present more, but I ran out of time. But that happens in life. But I hope that was helpful. Thank you.